those weren't bad because all they were talking about is adding the corresponding parts and then finding the transpose. And so I wanted to make sure I at least did a problem by hand with you involving finding the transpose, because we kind of did a lot of hand waving and calculator talk last time, but I wanted to make sure I hit it. So A plus B, figure that out first. Easy enough because it's just adding corresponding parts. So, well, easy enough conceptually. That doesn't mean I'm not going to proceed to immediately screw it up. It looks like 444 across the top. And across the bottom it looks like 666. All right, so A plus B transpose, so the transpose of A plus B would make row 1 into column 1 and column 1 into row 1, and the same thing with rows 2 and 3 and so on. So we're starting off with a 2 by 3. The result should be 3 by 2. So 444 down column 1 instead of row 1, 666 down column 2. And you can see that it kind of checks out conceptually because if I take column 1 in A plus B and make that, just turn it, that would become row 1. And same thing with column 2 and column 3. They would become 4, 6 horizontally instead of 4, 6 vertically. All right, so that seems to be consistent one way or the other. And again, something that's very easily verifiable with your calculator. So then the transpose is added. So first I'd figure out the transpose of A, which is just 1, 2, 3, 4, 5, 6. And then the transpose of B, which is 3, 2, 1, I think. 3, 2, 1, 2, 1, 0. And then add your corresponding parts, and you'll see you get the exact same value, matrix. So pretty easy to verify, and also pretty easy to construct a proof for. If I asked you to do that, it wouldn't be too crazy, because if I wanted to do it as a proof, what I would have to do is define A and B as 2 by 3 matrices. All right. And so with that being said, you would just designate A as being A11, A12, A13, A21, A22, A23. And then you do the exact same stuff for B. And then you just carry out the same set of processes. All right. So if I wanted to, I could just do the A plus B transpose, for example, just so I don't go too crazy with this. But just kind of carry it on over here. A plus B transpose. I would take the sums. So I first find A plus B just like I did before. which would be A sub 1, 1 plus B 1, 1. It's just a lot of writing, but not difficult writing. It's just difficult physically, not mentally. Like you physically have to do the writing. And then if you're anything like me, concentrate on not screwing it all up just by missing something fundamental. So A 1, 2 plus B 1, 2, A 2, 2 plus B 2, 2. A 1, 3 plus B 1, 3. A 2, 3 plus B 2, 3. And then the transpose of that easy enough, you're just writing it vertically. Even I'm getting writer's cramp. All right. Now, at this point, the thought is that instead of working the right-hand side and just kind of reinventing the wheel, you know, like just doing everything that we did with the previous, you know, the numerical case, the thought is that perhaps you can take what you have here and work backwards and disassemble it so that it's equivalent to A transpose plus B transpose, all right? And so if you were to disassemble this, you could see you have plus signs everywhere. You could actually make this, well, it really is what we need it to be already, because this is the transpose of A, right? And this is the transpose of B. So this actually is equivalent to the A transpose plus B transpose. So it's actually already there. We wouldn't actually have to do anything with the right-hand side. Here numerically, it's kind of like, well, how do you unadd the 4, 4, 4, 6, 6, 6? You know, it could be the array of values that were given to us, but it maybe not. I mean, it could be like to get a 4. There's infinitely many ways you could add two numbers to get a 4. But once it's shown as two separate sums, or two separate components of a sum, then it's already given, right? Because you're looking at this and say, well, this notation is telling me the transpose of what I really want, all right? So, and that's why I was harping on the notation last time, because if this were the correct notation, going down a column, this should be A11, A21, A31, all right? But that's not what we have, it's the reverse. So this must be the transpose of A. Fun fact, we already know that because that's what we did to get it into this form. But this is the sum of the transpose of the A's and the transpose of the B's, and so we have it, you know? And so as a proof goes, it's not terrible conceptually, it's just a lot of writing. It's fun though. I'll give you that. It's definitely fun. But it's a lot, right? So then I wanted, like I said, I wanted to touch on this, the transpose of the product of A and B, because this is the sum of A and B. But, and you know, I'll even take this as a typo, because I don't think unless I'm missing it, you know, because I'm skipping enough problems today where maybe I'm just skipping over the problems where this is relevant. These properties, but this one would be a logical one to have an example or two for. So I'll take it as a typo, create or include example for, or include new example on page 46. That's good enough for me. I'll know what that means. All right. So I need, and we'll just work with square matrices. I'm going to let A equal A11, A12, A21, A22. So we're keeping them square, 2 by 2 square matrices, so nothing too crazy. Now, I understand, looking at it in general terms, you might look at it and say, well, what do you mean nothing too crazy? We're not putting numbers in. Anytime you're not putting numbers in, it's automatically crazy. I respect that. All right, so the first thing I'm going to do is find the product of A and B. All right, so that's the process of multiplication. Now, 2 by 2 against a 2 by 2 is going to give us a 2 by 2. So we know that we're going to have a few calculations here that need to come into play. We're dotting the row against the column, so we're looking at A11, B11 plus A12, B21. All right, so that's going to be our first entry. That's this one. Second entry, multiply these guys. So A11, B12 plus A12, B22. Then A21, B11 plus A22, B21. Oh, I did purple already. Get a nice green going here. A vibrant green. A21. It's visible, right? Okay. B12 plus A22, B22. So I need the transpose of that, which is not terrible. It's just writing again. A, B, product, transpose. So rewriting the first row as the first column. All right. So. It's very easy for this to just look like jumbled numbers and letters on a screen, so I'm just going to do a quick double check across this row. I should have that column. So 1, 1, 1, 2, 2, 1, and then 1, 1, 1, 2, 1, 2, 2, 2, 2, 1, 1, 1, 2, 2, 2, 1, and then 2, 1, 1, 2, 2, 2, 2, 2. Okay. So somehow this matrix has to be equivalent to the transpose of B multiplied by the transpose of A, right? But honestly, I think we already have it, right? Same idea as the last one. Because if you kind of follow the program that was developed based off of the act of multiplying A times B initially, we really kind of established the framework for what an expansion of a product looks like. Right? So all we want to do really is just kind of undo that, but represent it in terms of transposes. All right? So one thing that we would not necessarily want to do or end up coming up with, I would think, would be what we started with. That would put us right back in a big circle. But what we can do is take this and really just unmultiply, so factor it. And we're going to learn a variety of different ways of factoring, but some of it just boils down to common sense. All right? So you have a pathway that was sort of laid out in front of you. Now it's just a matter of breaking up that pathway into factors that make sense. All right? So we have a dot product, and this is the result of that dot product. Right? Each one of these is a result of the dot product. Now, when I multiplied A times B, I took the first row and multiplied it by the first column. So when I evaluate this first expansion of the dot product, what I'm going to get, all right, yeah, it's supposed to be the B transpose first, not the A transpose. Right, so this has got to be the product of B11. So the B11 part has to come first. And then A11. And then B21 has to go here. And then A12. It helps if you remember what it is that you're trying to prove. Just a thought. You probably don't need that reminder, but I constantly do. We're looking to prove that it's equivalent to the transpose of B times the transpose of A, and we know that multiplication is not commutative when it comes to matrix multiplication. All right, so the B transpose part has to come first before the A. So we got a row and a column. All I need is one more row and one more column. So we'll have 3 other avenues in which we can come up with another row and another column, and then whatever one we use, the other 2 we can use to check. All right, so I'll use this one. All right, so in order to get this entry, I would have had to have multiplied B12 by A11. Right, so B12 by A11. So that checks out. Okay, and then the other one would be A12 by B22. Right, so in order to get that last entry, so this term here has to be B22. But honestly, with the transpose, that kind of has to be the case anyway. Because if you were to transpose rows and columns, we're really just looking to make this into that and this into that. The diagonals are going to stay put. I just want to verify, going through this process, that this is logically going to follow from the work that I've already done. All right. That's really all this is, because I already know what the transpose is supposed to be. I can carry out the multiplication. I just want to see that it's going to follow logically from this work. All right, so then I would look at the third one and say, in order to get that, I would have had to have multiplied B11 by A21. All right, so that makes this cell here A21. And then I would have had to multiply, in order to get A22, B21, all right, I would have had to multiply the A22, which I don't have yet, by the B21. So that means that that last cell has to be A22. And then it should check out for the last one that A21, B12, so if I'm carrying out this multiplication correctly to get that last cell, so B12, so I looked at the wrong thing. So B12 times B12, B22 imposed upon A21, A22. So B12 against A21, so I got that. And then B22 against A22, I got that, all right? In a dot product, the multiplication is commutative, so that works out perfectly fine, all right? And so what we come up with, because we know that this is the transpose of B multiplied by the transpose of A would be equivalent. So it does check out. We've already learned all the skills necessary to do it. It's just a question of, all right, under what circumstance would an inverse be useful? But isn't that the case for everything? You know, like we're learning all these skills, like why are we learning? You know, and we'll apply it. We'll look at the graphs and we'll really kind of dive in deep and see what the story is. But for now, it's just the skill. So I will preface this by saying your calculator is fully capable of easily finding the inverse of a matrix for you without doing any of the stuff that I'm about to do. However, on the test, I am going to ask you to find the inverse of a matrix by hand. All right. So we're going to be bringing back our good old friend, row reduction. All right. But I'll just show you real quickly. So I have 1, 2, 3, 5. So 2 by 2 matrix, 2 by 2 square. So 1, 2, 3, 5. Quit out of here. Finding the inverse of the matrix is as simple as calling up the matrix. And you know how we go into the matrix menu by hitting second inverse? That X negative 1 key? Yeah, fun fact, don't hit second. That's your inverse. It'll do it for you. All right? So, yeah. That kind of sucks because knowing that it's as easy as that on your calculator, same thing with matrix multiplication, but yet you're going to have to do it by hand. It's just, why does this need to happen? But, you know, we also think about all the things that I let you off the hook with, and so you're kind of like, it's all right to do something by hand every now and then. Right? So, in this rule here, the inverse of A multiplied by A is equal to I, and also the commutative property variation of that. That's nothing new. It just go back to basic algebra. If you multiply two inverses, the result is always equal to 1. That's the whole point. That's why it's called multiplicative inverses. And the I was the multiplicative identity. It's the same idea here, right? So if I multiply inverse of A by A, the result should be equal to I. I just got to figure out what that other matrix is, that inverse matrix is, that when multiplied by A will give me the result of I. Well, there's a couple of ways I could do that. One way would be to do the thing that I just did on the previous page, which, well, 2 pages ago, whatever it was. You know, make a new matrix. You know, we could call it A sub, or inverse of A with values A sub 1, 1, A sub 1, 2, A sub 1, 3, no, 1, 3, geez, now I'm just making stuff up, 2, 1, 2, 2, and then perform your matrix multiplication, which again is just your inner products. So A times the inverse of A 2 by 2 square matrices, it doesn't matter what order you do them in, it's going to be fine either way. We're going to be looking at A sub 1, 1 plus 2, A sub 2, 1 equals 1. Then A sub 1, 2 plus 2 A sub 2, 2 is equal to 0. A sub, 3 A sub 1, 1 plus 5 A sub 2, 1 is equal to 0. And then, yeah, Kev.
Isn't it A sub 1 plus 2A sub 2, 2?
Probably. A sub
2, 1.
2, 1.
Yeah.
This is getting multiplied by that. So 1, 1, and 2, 1. And then this is getting multiplied by that. So 1, 1, 2, and 2, 2. And then this is getting multiplied by that. So 1. I think it's right. Yeah, because it's getting multiplied by first row by the first column, 1, 1, and 2, 1. And then by the second column, so 1, 2, and 2, 2. And then the 3, 5 is getting multiplied by the first column, so 1, 1, and 2, 1. And then it'll get multiplied by the second column, so 1, 2, and 2, 2. All right, so we have this lovely looking system. just glorious. Really. Stunning, even. You can look at it a variety of different ways. You could just make up new words for it every step of the way. It's just.
3A, 1, 2, the last one.
For the last one? Yeah, 1, 2, thank you. So we would go through the process, and I'll just kind of spoil it a little bit for you. We have 4 variables. It's really a 4-variable system. We could actually rewrite each one of these matrices, each one of these linear equations, so that it includes all 4 of the variables. We didn't do this with the last example, but we could do it and come up with an augmented matrix that's just glorious. It would be splendid. Right. The other option is a little nifty shortcut, which I'm actually going to prove to you next class as to why it works. Or what you can do is take matrix A and augment it with I. Meaning, rewrite matrix A 1, 2, 3, 5 and augment it with the identity matrix. row reduce this so that A goes down to the identity matrix. And when that happens, I will emerge as the inverse matrix of A. All right, so what's going to end up happening is you'll get a new matrix through the reduced row echelon form technique, the Gaussian elimination of I augmented with the inverse of A. So what's going to happen is we're going to be reducing this down into R ref. We're going to go for the identity matrix here, and in doing so, we're going to be manipulating this with the same set of elementary row operations, and that's going to put this 1, 0, 0, 1, and it's going to create a new matrix, and that new matrix will emerge as the inverse of the original matrix A, right? So you could solve this system like we did 2 pages ago. There's nothing wrong with that. You know, if I ask you to do it using a by hand approach, I mean, we've already taken care of this approach. We've already done something like this. No need to do this one again. You could do this on your own if you want. Or you could try this technique. I think you'll find this new technique to be a little simpler. Because bottom line, you still have to go through the process of doing it by hand, where the previous one, the previous technique is going to be pretty easy to solve once you have your system set up. You still have to set up the system. This one is going to be easier to solve once you, well, maybe it won't be maybe it won't be that easier, but you won't have to put too much thought in coming up with the augmented matrix to begin with. All right, so there's a little bit of a trade-off, but it's really up to you to decide which way you like better. All right, so here I would just do -3 R1 plus R2. So 1, 2, 1, 0 staying put. But we're looking at 0. -6 plus 5 is -1. So -3. And then 1. Negate R2. And then just do a -2 R2 plus R1. That's going to give me, I'm just double checking to make sure I actually negated R2. So I have 0, 1, 3, -1. So 1, 0, negate, and I'm sorry, multiply 3 by -2, you get -6 plus 1 is -5. And then 2. I don't know, hopefully that's what the calculator said. All right, because left-hand side is now down to the identity matrix. So this is now, the way we note that is by calling it I sub 2. You'll see that in some other problems here and there. But identity matrix in 2 dimensions, because identity matrices are always going to be square matrices. So you don't have to say it's 2 by 2. If you just give me 1 dimension, I know it has to be for both rows and columns. All right. And so that's telling me that the inverse of A is equal to -5, 2, 3, -1. All right, and that's a technique I just need to know. Okay, good. Thank you. Because after all those coughing fits, I just needed a win.
I didn't plug it in, but I ran it the other way.
Right. So we have our inverse matrix. But you can see the next example is pretty much the same idea, so you can practice with that. And here what we come up with is a generalized rule that allows us to make a determination of what the inverse would be for any matrix. All right, and so if you don't do this one, that's fine. If you don't do the second one, that's okay. Definitely try this one, the one in general terms. All right, I'm not guaranteeing that that's definitely going to be on the test. But, I mean, if like my mental state right now or a seesaw, it's like, and downward is in the direction of being on the test, I mean, it's like right here. Like it's not on the ground, but it's like right there. Like I really want to put that on there. I don't know if I'm going to end up following through on that claim, but I mean, it's a good one. It's a good proof type question to have on a test, I think, personally. Question?
It was you're talking about the first one.
Oh, this baby right here, yeah. That juicy one. The case that involves the letters is going to provide us with a general rule, which already spoiled is on the top of the next page. But then we could use that rule to deal with any other 2x2 square matrices. All right, so if I want to tackle this kind of problem, I want to augment the matrix with an identity matrix in 2 dimensions. So that was the last easy step in this process. Actually, it's not too crazy because there's only 4 entries, but we do have to row reduce A, B, C, D down to the identity matrix. All right. So one way that you might want to consider doing it would be just right off the bat, divide the first row by A. I don't know that I'm definitely not going to do that first. Because it's going to introduce a fraction of 1 over A in the identity part. But you could make the A into a 1 immediately, but then you're going to make a B over A, a 1 over A, and you'll have to work off of that. Right? I'm just going to suck it up and say, listen, I got to make the C into a 0. So what I'm going to do is I'm going to take row 1, the pen turned off. I think my pen's not turning off. I think I'm turning it off just by like writing. Because I think as I'm writing, I'm putting so much pressure on it that I get a powerful grip, and that's really what's happening there. So it is what it is. So 1 over A, row 1. Now 1 over A, row 1 isn't going to cancel the C unless I multiply that by a negative C. So I'm just going to kind of tuck it in here. A negative C multiplied by that 1 over A, and then add it to row 2. I mean, it's going to be a holy mess no matter how you slice it, so it just is what it is. I just prefer to do it this way. You may disagree, and that is your right. All right, so we're going to have a 0. All right, so that's something. Then D, I wanted that to be in purple. D minus BC over A. Oh, that was there. Because I'm adding the negative C over A. I'm multiplying that by the B and adding it to the D. So this is going to become negative BC over A plus the D that's already there. I'm just putting the D in front. So then we're going to have negative C over A plus 0 is negative C over A, and then we'll still have the 1. So that's something. All right. Now, I'm looking at that second entry in the second row. I have D minus BC over A. I mean, I'm going to have to put that together at some point. So no time like the present. So I'll get a common denominator, multiply top and bottom by A. I'll just kind of chuck it in there. And so at that point, since I see each of my terms has a denominator of A, I'm just going to multiply row 2 by A. All right, so we'll have A, B, 1, 0, then 0, AD minus BC, negative C, and A. It doesn't matter what the augmented part of it becomes, the 1001 that we started with. That's going to be our inverse. It's the left-hand side, the square matrix on the left-hand side. That's got to become the identity matrix. So win, I guess, kinda. Doesn't really seem like it initially, but it's actually a step in the right direction, because even though it doesn't seem like it would make sense, we could actually make that AD minus BC into a 1 right now. Just divide it by AD minus BC. All right, so we're in good shape there. It's just, it doesn't feel like we've accomplished much of anything, but we're actually, and you know, there's no reason why you can't keep an eye on what the formula is supposed to look like. There's an AD minus BC in it, right? So that's something to keep in mind. And actually, if you have any experience with, if you had any experience with matrices before this course, if you're looking at a 2x2 square matrix, you might recognize AD minus BC as being the shortcut rule for finding the determinant of a 2x2 square matrix. All right, so this is a very valuable piece of information. All right, so again, just like before, it's a question: do I want to divide it out now? It's going to get ugly. Do I want to do it now, or do I want to do it later? All right, if I do it now, it'll clean this up, but it'll make this ugly. If I do it later, I'll have to work with this now in order to somehow cancel that. All right, so one way or the other, you're on the hook for it. All right, so I'm gonna leave it as is for a sec, because we can actually make our way through with this, and it's not gonna be as terrible as it seems at first glance. All right, so I want to cancel the B, so I'm gonna multiply row 2 by negative B, but I need the AD minus BC to go away. Plus row 1. All right, so AD minus BC on the bottom is going to kill that AD minus BC, and by multiplying by a negative B, it's going to make it into the opposite of the thing that I'm trying to cancel, which is ideal. What I'm going for. First entry is still going to be A. No change there. But now we have a 0. I just wanted that to be red. A. I'll just kind of smidge it over a little bit. Let's do it there. A, 0. All right, this is the part where we have a little bit of work ahead of us, but we're really just taking 1 and adding it to BC over AD minus BC. So 1 plus fraction BC over AD minus BC. And then the last piece, I don't think, yeah, I put that in there too quickly, so it is what it is. I'm just going to have to smush it in there. The last piece has me taking the A and multiplying it by negative B and adding it to 0. All right, so negative AB over AD minus BC. So negative AB over AD minus BC. Bottom row is going to stay put for the next minute or so. So we're looking at 0, AD minus BC. And then we have the negative C in the A. This does not seem like we're in the home stretch, but we are. All right. I'm still not going to divide by A, though. I don't want to do that yet. What I'm going to do is kind of on the fly get a common denominator here. So that 1 is really AD minus BC. I'll just kind of chuck it in over here. Over AD minus BC. So from that, or adding to that, we have a BC. So I have an AD minus BC plus BC. So those negative and positive BCs are going to cancel out. All right. And the reason I say I'm going to do it on the fly is because I don't want to waste a step. I don't want to rewrite the whole thing just to conclude that this is going to be AD. I would rewrite the whole thing just to write, instead of this, AD over AD minus BC. All right, I don't want to write it that way, or I don't want to take the time to write that extra step. But this is my new fraction. All right, it's in this step. Now that I've cleaned that up, that I would say, I get an A across the board in each one of my numerators. Now I'm going to divide row 1 by A. All right, so 1 over A, blue. 1 over A, row 1. So we'd be looking at 1, 0, D over AD minus BC. Negative B over AD minus BC. On the bottom, I got all of this crap. But you know what? I don't want that there either. I don't want the AD minus BC anymore. So simultaneously, I'm going to do a 1 over AD minus BC on row 2. And that's going to give me a 0, 1, negative C over AD minus BC, and a positive A over AD minus BC. All right, so I achieved my objective of getting the left side down to the identity matrix, and the right-hand side ended up being, well, this is the inverse, but it's a hideous mess. But really, it's not that hideous, right? Because we have a common AD minus BC. on the bottom. So we'll factor it out. All right, so we'd be looking at 1 over AD minus BC multiplied by D negative B negative C A. Which happens to be the rule that's detailed on the previous page, or the next page. That is the shortcut rule for determining the inverse of a 2x2 square matrix. And you look at it and say, well, that sucked. Why? I'm never going to use that formula. But then you realize, well, you don't have to do all that work in order to use a formula. It's not that bad. So if we go back to that previous example, I'll just pull it up, 9473. And we want to find its inverse. You just have to identify the A, B, C, D values. All right. All right. So we're looking at 1 over 9 times 3 minus 4 times 7 multiplied by, well, the A value and D values are going to get swapped, so 3, 9 instead of 9, 3. And the B and C values are going to get negated, so negative 7, negative 4. So really the only computation in here is this determinant part. All right, so this ends up being the determinant of matrix A. I'm just calling it matrix A. I don't know what it's defined as. It could be anything. But whatever the determinant of the 2x2 square matrix is, that serves as the denominator of your coefficient. So that's this part. And we're going to do a whole lesson, 2 lessons. Oh, well, the rest of the course is going to involve the determinant in some capacity or another. So you're like, what is the determinant? We'll get there. So 27 minus 28. Well, that's anticlimactic. So negative 1 as the coefficient. And so our inverse would be negative 3, 4, 7, negative 9. And that's something you could easily check with the calculator. The formula itself is pretty easy, but strictly based off of your ability to use the formula correctly. Definitely easier than doing the row reduction. Problem is, and there's a limitation to this formula, only works for 2x2 square matrices. Row reduction is going to work for everything. Right? Anything that is invertible is going to have a solution through row reduction, but not always through the shortcut rule. So that kind of sucks. So you're limited, but you come across a problem along these lines, even if it involves variable quantities, you're still going to be able to use this technique as long as it's a 2x2 square matrix. Right? But it definitely needs to be invertible, and we'll talk about what that means in a few minutes. We were using row reduction techniques to find the solution of a system. Turns out if we knew how to find an inverse, then we could actually use that technique to find the solution also. All right. Now you might look at it and say, well, if I have to use row reduction in order to find the inverse, then why don't I just use that to find the solution of the linear system? My answer to that is, well, I'm not always going to make you use row reduction to find an inverse. The only time I'm going to make you use row reduction is when I tell you you have to use row reduction. So if I give you a word problem here that says, write the system of equations and then write a matrix equation and solve. You do it any way you want, as long as you're using an appropriate technique. Right? You may choose to use row reduction at your own risk, but if you go back to the first unit when we were talking about the non-homogeneous linear systems, AX equals B, it was all row reduction, but we used the calculator. Right? Here we're going to use a calculator. We're going to use the inverse function on the calculator. We're just going to kind of use the functions in a different way. All right, Megan paid $39 for 3 pounds of pistachios and 2 pounds of cashews. Tanya paid $23 for 2 pounds of pistachios and 1 pound of cashews. Write a system of equations where X represents the cost of a pound of pistachios and Y represents the cost of a pound of cashews. Then write a matrix equation and solve. So the setup, I mean, there's nothing unique here. We've been down this road before. Choose your variables. Choose wisely. You choose anything you want. So I'll just go P and C. Cost. Oh no, we don't have a choice. I read my own problem there. X represents so I don't have to write let anything. X is the cost of a pound of pistachios, and Y represents the cost of a pound of cashews. All right, so we have 3X plus 2Y equals 39. And then we have 2X plus 1Y, or just Y, is equal to 23. All right, so if I write this as a matrix equation, it would be, now normally it's AX equals B, but we're using Y here in place of X2. So it's kind of loosely AX equals B. So 3, 2, 2, 1 against XY is equal to 39, 23. All right, so this problem really gets at the motivation of why we learn about inverses to begin with. Because, like, say you're in 2nd or 3rd grade, you learn about multiplication. Before too long, you learn about division. All right, addition. Before too long, you learn about subtraction. All right, converting from decimals to percents. Before too long, it's percents to decimals. It's always one way as opposed to the other. The opposite operation is the inverse. At no point have I talked about anything known as matrix division, and that's because there is no such thing. All right? What we have is matrix factorization, which is an implied division, and we have inverses, which again are opposite operations. So if I find the inverse and multiply with that, that's the same conceptually as dividing. All right? So what I would do here is I would take that 3, 2, 2, 1, I'd swing it to the other side. And slap an inverse on it. Because that's what's going to make it division. All right? That's what's going to make it isolate itself from the XY. But then I'm going to multiply. I'm going to use matrix multiplication between that and the 39, 23. All right, so I'm gonna calculate. So I put in my editor, matrix A, it's a 2 by 2. I don't have to find the inverse by hand. I'm going to put in my solution vector as a new matrix, a 2 by 1, 39, 23. And then all I'm going to do is multiply, hit the wrong thing, repeatedly hitting the wrong thing, matrix A's, I'll get there, names, matrix A's inverse by matrix B. All right. So then, oh, by the way, I kind of glossed over something, but I just figured I'd make the statement before too much time has passed. If you're wondering why I chose to put it in front of the 3923, it's just because of the rules of multiplication. And if I put it the other way around, it would be a non-starter. The number of columns here would not equal the number of rows. I would not be able to multiply. The shorter answer is if I did it the other way, calculator would give me an error. All right, that's an acceptable reason too. All right, so you get 7, 9. All right, so is it any easier than using reduced row echelon form? I don't know, probably not. Because if you really think about it, with ref, you're typing in one matrix. With this, you're typing in 2 matrices. But what you're doing after that isn't bad, one way or the other. They're both pretty nasty if you had to do them out by hand. So I guess that's a saving grace for anything. Most people are just happy in this course to do pretty much anything I ask them to do because they know that the trade-off is doing it all by hand. If anybody's ever had any experience with linear algebra with like in another environment, you know that it can be like calculator. What calculator? It's pretty crazy stuff, right? So those proofs that we were doing before, that's like all class, every class. So I like doing those, but I like doing it on my time. I don't want to go too crazy with that stuff. All right, so should probably answer the question, you would think, right? So we are looking for the total cost. So we're looking at $7 per pound of pistachios. That's outrageous. Honestly, I have no idea. I've been out of the pistachio market for quite some time. And $9 per pound of cashews. Actually, cashews I know a little bit about. Those are like ridiculously expensive. I only know that because I used to go nuts for the chocolate covered cashews, like at Costco. They would have like the big jumbo size. I'd kill those in like a weekend, which is like horrifying because like what it's doing to your, like you eat that much nuts, like what it's doing to your insides is like just not good. So yeah, but I would destroy those things, and it would be like $10 for like a big jammy of those chocolate covered cashews. I'd just tear into them and just go crazy. And then one time I didn't have an opportunity to get over to Costco, so I went over to Stop and Shop to get some chocolate covered cashews, and it was like $15 for like a small canister, and I'm like, that's just insane. So I know cashews can be a little on the pricey side. I didn't know pistachios ran that much though. I don't even like pistachios.
Aren't they even more expensive?
Are they?
Yeah, they are expensive.
Well, I don't like them anyway, so it works out nicely. Somebody gave me some pistachio ice cream once. I gave it right back to them. I'm like, who do you think you are? Like it was like an insult. You know, I'm very particular about my my choices and treats because like people come up to me, they're like, oh, I got you something, and it'll be like chocolate covered, and then if Lord help you if you say the wrong next word, like chocolate covered. Yeah, I could do those. Those raisinets, I like those raisinets. But then you have like throw in something else, like something weird, and it's like, what? Why are you doing this? You know. Although one time I almost had that reaction. I didn't know. I didn't know how delicious macadamia nuts were without chocolate on them. Like I just thought, like they're always part of like a like white chocolate macadamia. It was always like part of it. Yeah, and in the it always went with something. And somebody handed me some macadamia nuts, and I'm like, oh, thanks a lot. You know, like what a treat. They're like candy themselves. Like it's insane. I mean, I didn't know I didn't know that something could grow naturally that could actually taste like that. And I like that was something. But yeah, you come at me with something. The same thing with like holiday gifts. I've had people come up to me and be like, oh, I got you a new coffee mug. Like, oh, I really appreciate it. Is it machine washable? And they're like, no. And I'm like, I appreciate the thought. I'm sure somebody else will take this like fly-by-night nonsense that you tried passing off on me. Like, give it to somebody else because if I gotta wash it by hand, I don't want any part of it. There's garbage, swell bottles and Yeti cups and stuff like that. Like Yeti, you pay freaking $70 for a mug or whatever it is. Like, I went to Target, I got one that says nice. It said nice on it. It looked exactly the same. It was $13, and it's machine safe. That's what I'm talking about. Like, if you don't mess around, you could have your cake and eat it too. That's what it all comes down to. So you don't have to settle for pistachios if you don't like it. You could have cashews. I also am fond of chocolate-covered almonds, but not. I mean, these things I like destroy them. Like it got to the point where if somebody offered me a chocolate-covered cashew, I'd be like, nah, can't do it. I have PTSD from it. It's like insane. So the next one is pretty much the same deal. So I think I'll just leave that for you. That's my way of saying I think I talked a little bit too much about chocolate covered.
You should try the chocolate covered raisins
From Costco?
Huge jar.
Add it to the list. Add chocolate covered raisins to shopping list.
Okay, added.
All right. I gotta make a Costco run anyway, so I'll be hitting those babies up.
The best thing is if you don't like them, you can always bring
Beating a dead horse, I think, which is really an archaic expression. I should probably stop saying that. So these are important. We'll get to that in a second. But the algorithm for finding the inverse, we've kind of talked this to death. It's row reduce, create the augmented matrix, row reduce until you get it into reduced row echelon form, and then you'll have your inverse. All right, so this one I would say is more for practice than anything else. So I'll put a star on it. But these rules are very important. Some obviously more important than others, and I kind of attach importance to concepts based on whether or not I can naturally remember them. All right, so I'm thinking from a student standpoint. If it's something that I look at as like, that's common sense. Okay, so that's not an important rule. Now, it might be really an important rule. Like the reality is in mathematics, it might be an incredibly important rule, but in my life, it's not important because I don't have to worry about that because I can look at a situation and say, well, that's definitely a true statement. Like multiplying a matrix by its inverse is going to give the identity. All right. Now, you may look at this and say, well, maybe that's common sense to you, pal, but for the rest of us, it doesn't make sense at all. Well, take a simpler situation. Take 2 and multiply it by its inverse, which would be 1/2. The result is 1. 1 is the multiplicative identity. All right, so you're taking a number, multiplying it by its inverse, and getting the identity. All right, so this is no different except we're using notation. Obviously, we're using matrices. Another thing that allows me to attach personal importance to something is whether or not the calculator is going to figure it out for me. All right, A times inverse of A. All right, so if a question came up and said, determine whether this is a true statement. Well, I'm going to put it in my calculator first, try a few different cases and see if it ends up being a true statement numerically before I start getting into a proof. All right, because if it doesn't work out numerically, odds are it's not going to work out in general terms. All right, so this one falls into the realm of common sense. This one, not so much. You wouldn't necessarily, I don't know, think that this is the case, or maybe you would, but maybe you weren't sure, but it definitely is the case. This one probably makes more sense now that we went over that proof earlier. But if I just led off with this today and said, well, here's a rule, does it make sense to you? You'd be like, no way, all right? But based on the fact that we talked about transpose before, if you multiply 2 matrices and then take its transpose, then that's the same as the product of the 2 transpose, but in reverse order, all right? Well, isn't a transpose really, if you think about it conceptually, kind of a form of an inverse, right? You're talking about a reversal in some capacity. You know, maybe it doesn't fit every definition, you know, it doesn't hit all the bullet points of the definition of an inverse, but if you're talking about opposite operations, we're taking rows and columns and switching them, all right? That is, in effect, what an inverse is talking about, changing the process. Back becomes front, left becomes right, up becomes down, all right? So it kind of, in that context, makes sense that this rule would follow the same rule that we developed earlier based on the transpose, all right? Properties of the inverse. There's a lot. And really, any one of these can be a proof. Some of them are a little bit more obvious than others. Identity matrix I is invertible, and the inverse of I is I. Right? I think that one is probably along the lines of common sense. All right, what's the inverse of 1? 1. All right, if you're talking about numerically. So, you know, identity matrix serves as the number 1 for matrices. So why would that be any different? All right, the inverse of an inverse. The enemy of my enemy is my friend. Right, so that's the same idea there. If A and B are invertible matrices, oh, this is one I already talked about. If A is an invertible matrix, then so also is A to the K. All right, so we're gonna have to talk about that in a few minutes, right? Because we can take a matrix and raise it to a power, all right? So if I were to take a matrix and raise it to the 2nd power, you're multiplying a matrix by itself. That's easy enough, all right? But if I raise it to the 10th power, I would like to think that you probably are not overly interested in taking 2 matrices, multiplying them together, taking the answer, multiplying it by a new matrix, and then a new one, and then a new one 10 times. All right, so there's got to be a shortcut to that. So we'll get to that in a little bit. Some of these, again, are just kind of a rehash of things that we already know. Some of these are talking about stuff we haven't covered yet, so we'll get to that also. Number 12, very important. If A is an invertible matrix, then the matrix equation AX equals 0 means that X equals 0 is the unique solution. All right? AX equals B means that this we actually already talked about. But this is telling us that the unique solution, you know, you're thinking of a homogeneous situation. If it's an invertible matrix, then the unique solution, the one that exists that is not dependent on any other situation, is going to be the 0 matrix. All right? So that's something that, you know, it's kind of counter to what we were dealing with the homogeneous case, because we weren't focused on whether something was invertible or not. All right. So these are some properties, but then on the top of the next page, it's the invertible matrix theorem. Characterization is another name for it, but I'm going to wipe that out. And it's not really a typo, but I'll take it as a typo. This is actually a theorem. And I would say that this is probably most folks' least favorite theorem in this unit. Even though a lot of it's common sense, I don't even know what I was trying to do there. Even though a lot of it is common sense, it's not something that pops out in your mind as, wow, I really want to memorize that. Or I really want to write each of those things down on my index card for the next test. You know, it's a lot. So the invertible matrix theorem tells us that each one of these bullet points are equivalent, which means that they're all the invertible matrix theorem. So which part is relevant? Well, it depends on the situation. So invertible matrix theorem tells us that if you have an n by n matrix, so square matrix, it's going to be invertible as long as all these other things are true as well, right? Or any of them are true because they're all equivalent. A is the row equivalent to the n by n identity matrix, meaning you could put it in reduced row echelon form and get it down to the identity matrix, all right? So it has to be equivalent when you ref, and this is probably the most important piece. If you keep this in mind, you could probably never go wrong. If you're given A, if you ref matrix A, in n space, right? So meaning that you could have any number of dimensions, right? But it's still going to be a square matrix. Result must be the identity matrix for that particular dimension. All right. So if you're dealing with a 4 by 4 square matrix, then it must row reduce down to the identity matrix for a 4 by 4 square matrix. Which means that every column is a pivot column, even the last column. All right. It only has a trivial solution. All right. These are all things that would come into play. If it only has a trivial solution, that means that the column vectors are linearly independent. We learned that in the last unit. The only way that you can justify independence was to show that the homogeneous equation only had the trivial solution. All right, so these are all things that we know. Linear transformation is 1-to-1. All right, so that means that it's not going to map to multiple destinations, or multiple destinations are not going to map to the same matrix. All right, the equation AX equals B has at least one solution for each B in Rn. Right, columns are a span. Right, same idea. Right, the at least, just going back to this one, at least one solution. Well, we already know one of them is going to be the trivial solution, because part of the non-homogeneous solution is the solution to the homogeneous case. So that's really all that's saying. It's just kind of reiterating that you will have the trivial solution plus any other dependent solutions that might exist. All right, which also, I mean, when you're talking about solutions to a homogeneous system and the columns of a span, you're really talking about the same thing. Linear transformations. These two are interesting. There is an n by n matrix C such that CA is equal to I. All right. So that's telling us, really, if you think about it, that you can have some matrix that when multiplied by your given A, your invertible matrix, that gives you I as a result. That makes sense, because that value, that other matrix should be the inverse, all right? And then the transpose of A is also an invertible matrix, all right? These are all things that would be true, right? This is weird because it seems like it's a repeated concept, but it's not, because it's saying this is really just addressing the concept of the commutative property. Because remember, multiplication is not commutative for multiplication is not commutative for multiplication. Fun fact. The American Dodgeball Association of America. Yeah, sometimes I do that. Multiplication is not always commutative, but the one time it is commutative is when you're multiplying a matrix by its inverse. So you can multiply it in either order is really all this is saying. Right? So it seems like a repeat, seems redundant, but that's really all that's going on there. All right, so you have two examples here, and these are some, not too crazy examples. I'll put some stars on them. It says use the invertible matrix theorem to decide if A is invertible. Now, that's why it was important that I changed the title here. So if you didn't change this from characterization to theorem, then you'll be one of the people that I had to reply to in the past that said, listen, I understood everything in class, but the question is asking to use the invertible matrix theorem. What the hell is that? We didn't go over it in class. Oh, it's a thing at the top of the page. It's the characterization. Oh, probably should have said that. Thanks for the heads up. So here I am saying that. All right. So in the case of A, and really anything could be a by hand question on the test. As you know from the last test, I'm not going to ask you to do everything by hand, but I am going to ask you to do some things by hand. Right? Maybe it's something like this. Right? Maybe it's something like that. You could conceivably ignore all of this stuff, put both of these matrices in your calculator, and use the inverse function. If you get an answer, it's invertible. If you don't get an answer, it's not. The problem is that's not going to help you if you have to do it by hand. All right? Well, it will, but it won't tell you why it's invertible. So for the first one, yeah, put it in the calculator. I mean, use the rule, use the shortcut rule. It's 2 by 2. If you get an inverse, you get an inverse. Fun fact, since the shortcut rule inverse of A, 1 over AD minus BC multiplied by DA negative B negative C. Very easily determine if a matrix is invertible based off of this calculation. All right, hold on. Let me see if I can do this. Just move it around a little bit and then write, and all of a sudden it doesn't smear it. So, AD minus BC, which again is this magical thing called the determinant that we haven't really talked about yet. But that AD minus BC can't be equal to what? 0. So if it's equal to 0, then you're looking at something that's not going to be invertible because you're going to get an undefined expression, right? So that could be a way of handling it. You could look at this and say, well, I'll just figure out the determinant. If I get a 0, it's not invertible, right? But then you look at this and say, well, where's my shortcut rule for the 4 by 4 matrix? And you say, well, guess what? There isn't one. Well, that's not true. There are rules. You may choose to call one of them a shortcut, but only as a default, because the others will be just so much longer that you'll be like, well, I guess this is the shortcut. It's like you're gonna drive to the West Coast, and you could either take Highway 66, which will take you like a month, or you could take every interstate, and yeah, that's the shortcut. It'll only take you 2 weeks driving, right? It's the same idea. Question?
So you said if it's AD minus BC is equal to 0.
Right, because that would make this fraction undefined. right? So we wouldn't get a solution, all right? So there are ways to figure out the determinant for this, and we'll get into that next class, but it's not going to be pretty. So this is where you would want to use the invertible matrix theorem. So I would look at it and say, okay, kind of rub my hands together and say, well, which one am I liking? Well, that's no help, right? A is invertible. If I knew that, I wouldn't be doing this problem. A is the row equivalent to the n by n identity matrix. We're on to something. Because what that's telling me is that if I row reduce that matrix down and I get the identity matrix, then it will be invertible. All right? So what that means is that I don't actually have to augment this with the identity matrix. So I don't have to create a 4 by 8 ginormous matrix. All I have to do is row reduce this down. And if I get anything other than the I4, all right? So our ref of matrix A must be equal to the identity matrix in 4 dimensions. All right. If I get that, then I'll know that the invertible matrix theorem holds and that this has an inverse. All right. Because again, this is an existence theorem, existence proof. It's not determining what the actual values are. All right. So I don't need the inverse. I just need to know whether or not one exists. All right, and we'll talk next class about why it's important to sometimes know just when something exists and not what it is. All right, and then with technology and brute force and stuff like that. So the last thing we're going to do tonight is called, it's LU factorization. It's pretty quick. But I teased this before by saying that we have no form of matrix division, but we do have a variety of ways of factoring. And one way was just by observing. I had an expanded form when we did one of those proofs earlier. We had an expanded form and I said, it must have been this times that in order to get that result. But sometimes it's a little bit more complicated than that. So the LU factorization is a particular algorithm. The L stands for lower triangular. And the U stands for upper triangular. So you have ones down the main diagonal in both cases. And even if you don't, you could always make it so that they are. Just with some strategic multiplications. A little asterisk represents some non-zero value. Right? So what a lower triangular matrix is just basically telling us that only half of the matrix, it's a square matrix, only half of it contains 0 values and everything else is some set of non-zero values. All right. So for a lower triangular, all the data is on the lower triangular part, 0's on the upper triangular part. All right. For upper triangular, all the 0's are on the bottom half, all the numbers, non-zero values are on the upper half. The algorithm. There's a lot to it, but there's kind of a procedure that sort of transcends what's written here, but I'll take you through it. It'll make more sense when we go through it. But step one is it's weird. It says begin reducing A to an echelon form, so to n echelon form, right? So not to the reduced row echelon form. So this is not putting it in the calculator. And if there is a way to put it in the calculator, it escapes me. Where we're going to begin reducing A to an echelon form U in such a way as to only replace values in column 1 under the main diagonal with 0's. All right, so that's already weird. Do this by a sequence of row operations if possible. Don't swap any rows. All right, that's an important piece. You need to highlight that, flag it in some capacity, any way that you're going to draw attention to it. You can't swap rows because that's going to impact the pivot values, and we need the pivot values to be where they are, otherwise the LU algorithm fails. Divide each entry in the first column of A by the pivot number. These will become the new entries in column 1 of L. All right, so it's already weird. Continue reducing A to an echelon form U in such a way as to only replace the values in column 2 under the main diagonal with 0. So this is the same as 1, except we moved on to column 2. All right, divide each entry in the second column of the previous iteration of A by the pivot number. These become the new entries in column 2 of L, and then repeat as needed for any remaining columns. All right, so it gets out of hand pretty quickly in terms of what the expectations are. So we definitely need to dive into an example, but I can tell you right now that all you need is once or twice and you'll have it. It's not as difficult as that process makes it seem. Although I am gonna just copy paste the process right on the top here just so I can point at it and laugh at it, I guess. I don't know. Emphasize certain points, I guess. Oh, that's not what I want to do. I haven't done that in a while. All right. So we want to factor this, LU factorization, but it just means that we're going to have a lower triangular matrix and an upper triangular matrix. All right. So, but it'll have the same shape as the matrix that we're given. So I'm going to define L and U. All right. So first step again, begin reducing A to an echelon form in such a way as to only replace values in column 1 under the main diagonal with zeros. All right, so focusing on column 1, that's this set of values. Sometimes it's helpful to actually put the matrix in reduced row echelon form right off the bat just to see where the pivot numbers are. But generally, we're looking at the main diagonal, all right, for a square matrix. All right, we'll cross those other bridges at a later date. I'll just put it that way. So I need to start the row reduction process. In order to do this, and I want to work with it as is. Right, I can perform operations, row operations. I just don't want to swap anything out. All right, but if I leave it as is, I want the 30 to disappear. What I'd have to do is simultaneously, I'd have to do a negative 1/60th R1, well, sorry, negative 30/60th, so negative 1/2 R1 plus R2. And then I'd also have to do a negative 1/3 R1 plus R3. All right, so this is going to start the process of giving us U. All right, we're going to row reduce down. 60, 30, 20, that's going to stay put. All right, we're just trying to get U to be upper triangular, which means I just need these values to go to 0. All right, the 30, 20, and the 15. All right, so that's what I'm going to do. So 60, 30, 20 is going to stay put. I turned it off. Getting in my own way now. If I take my first row, chop everything in half, negate it, and add it to the second row, I'm going to get a 0. All right. So chop this in half. Negative 15 plus 20 is going to be a 5. And then chop this in half. I'm going to get negative 10 plus 15, also 5. Do the same thing, but with a negative 1/3. So 0. Negative 10 plus 15 is going to be 5. The last one is going to be some fractional value because we're looking at negative 20 over 3 plus 12. So negative 20 over 3 plus 36 over 3, really, right? So 36 minus 20 is going to be 16/3. I mean, you do that in a calculator if you want, but we accomplished our first mission, and that was the process of beginning to reduce A to an echelon form in such a way as to only replace values in column 1 under the main diagonal with zeros. All right. Then we divide each entry. Well, we didn't do that, but then we continued row reducing to get U kind of going in the right direction. All right. Oh, actually, no, we only did that. Divide each entry in the first column of A by the pivot number. All right. Now, the good news is that's already kind of accounted for, because when we came up with the negative 1/2 and the 1/3, we sort of already did that. But that's going to give us the first column of L. All right. So my pivot number here is 60. Because we're assuming, now again, I have the benefit of experience with this. When you're dealing with invertible matrices, square matrices, it's gonna row reduce down into the identity matrix. So the pivots are gonna be right along the main diagonal. If you're not sure, then just put it in your calculator and row reduce it down. All right? If you get anything other than the identity matrix, then at least you know what the pivots are supposed to be. Question? Oh. So what I'm going to do here is I'm going to take every single entry in my first column and divide it by 60. All right? First one will be a 1. Then we'll get a 1/2. And then we'll get a 1/3. All right? Like I said, we already had those numbers. They were negated, but we had those numbers, the 1/2 and 1/3. We had them intuitively. All right? So this lower triangular matrix should have zeros on the upper half and all the numbers on the bottom half. All right, we're getting there. So now I'm going to move on to the second column. All right, but yeah.
Yeah, sorry. So you did this like when you divide by 60. This is the step number 3, right?
Yeah, exactly. So then we're going to continue reducing A into U form. So we're going to work off of this matrix now, but we're now on column 2. All right. So what I want to do is at this point, because I'm going to get a new matrix once I simplify this a little bit further. But here I want to make, and I'll just highlight it a smidge. I'll go red. Those keeping score at home. This is what I'm working on because, again, echelon form. So the values under the main diagonal have to be 0. Right? So I need this blue 5 to become a 0. So I'm going to do negative R2 plus R3. So row 1's going to stay put. Row 2 is going to stay put. Row 3 is going to become 0, 0, and then I'm going to take 5, negate it, so negative 5 plus 16 thirds. Negative 5 is the same as negative 15 thirds, plus 16 thirds is 1/3. All right, Now, once it's in upper triangular form, you're done with that part of it. So this is good. I don't have to worry about U anymore. All right, this is in its final form. Now I just gotta figure out L. Divide each entry in the second column of the previous iteration of A by the pivot number. These will become the new entries in column 2 of L. All right, but remember, L is supposed to be upper triangular. I'm sorry, lower triangular. So what I'm gonna do is I'm just gonna pre-fill the zeros where they ought to be, because I don't want to accidentally put some numbers in there where I don't want them to be. Right? So looking at this, just really it's the 5 and the 5. The pivot number is that middle 5. All this algorithm is telling me to do is divide each of these entries by that pivot number. So it's going to be 1 and 1. And then it says repeat as needed for any remaining columns, which is just telling me to row reduce more if I need to, I don't need to. Divide each entry in the next column, the third column, by the pivot number. Well, the last column has a pivot number of 16/3. All right. You could even go with, last column, I was looking at the wrong one, has a pivot number of 1/3. Well, it doesn't really matter what that number is because you're about to divide it by itself. So you're going to get a result of 1. All right, so that gives me my last entry. All right, so it's very systematic, but you get your L and your U, and if you carry out the multiplication of L and U, you're going to come up with matrix A. All right, and you can test it out. It's pretty straightforward. I mean, you don't have to test it out by typing it all into your calculator. Just take a couple of test examples. Take row 1 and column 1 multiplied. You see you get a 60. Take maybe row 3 and column 2. You'll see that you get 15. All right. So row 3, column 2, you get 15. So it checks out, at least for a couple of test cases. All right. Worst case scenario during a test, put it all in the calculator. You want to play it safe. Kev?
How you are getting L, the row, like 1/2, 1/3.
Yeah, so once you identify the pivot numbers in each column or each row, you can look at it either way. You're just dividing each entry in that column by that pivot number. So pivot number is 60. I'm dividing each one of these numbers by 60. 60 divided by 60 is 1. 30 divided by 60 is a half. 20 divided by 60 is 1/3. Then looking at this one, the pivot number is 5. If I divided each number in this column by 5, I'd get 6, 1, 1. But the 6 is irrelevant because it needs to be lower triangular, which means that the upper part of it needs to be zeros. So I would disregard the 6. All right. The last one, the pivot number is 1/3. I can divide each of these numbers by 1/3, but these two values are going to be irrelevant because, again, it's got to be lower triangular, which means that these entries automatically have to be zeros. So the only thing I'm going to be dividing by 1/3 is 1/3 itself, giving me the 1 there.
Okay.
So in that regard, I mean, it's very procedural, but if you follow the process, it's almost impossible to get wrong. All right, it's just you gotta make sense of the process. That's the one thing that can be a little iffy. All right. So I'm gonna put some stars because this usually every semester ends up being one of my more popular videos. So I'm gonna put stars on these questions. I do recommend that if you're a little iffy on this, you go home because everything makes sense in class and then nothing makes sense when you walk out the doors, that you watch the video